Okay, hi everyone. Can everyone see the slides? Okay, got it. So let me get back to what we have talked about last time. So we'll start a little bit from AlphaFold 2 version 2 and the general picture, just a little bit recap what we have discussed before. The first about input in terms of modeling protein structure. We have like two basic tensors, MSA and a residual by residual pairing, which so we have those two part of input, and we will update each of them through a module called Evolformer, and the Evolformer will take the alternative update and iterative update from both MSA to MSA to pairing and the pairing to MSA, and they are going iteratively after 48 Evolformer. And after those updates iteratively by MSA to pair residual by residual pairing, then we're coming to the structural model where the 3D structures are being predicted in that place. So last time we have talked about a lot of detailed design for Evolformer, MSA updates, row-wise and column-wise, and especially row-wise being updated by row-wise are being updated by a case called sorry, let me just jump to a case called pair bias. So in that case, where the row are being attentively learned, and we'll add a pair representation bias towards the MSA update. And most of the architecture are following the attention mechanism. The query value and keys are being specifically designed, and they are actually using, I believe personally, they are trying a lot of architectures, but they are voting for the most effective one. And so for today, let's get a little bit started from a little bit taste about the structure model. So in terms of structure model, last time we mentioned that in this case, we are taking the MSA part and the pairwise residual by residual matrix, and we are trying to really form the protein structure. So as you can see from the iterations here, it goes by the backbone updates towards each residual. And from this case, you can see every time it starts from every residual is centered in one place as the starter, and then you can see the protein structure are attached one by one generally. So this is we can see the alpha helix and beta sheet in the structure, and actually it is going one residual by one residual, both updating on the backbone structure as well as the residual atoms, so which are side chains. So a general conclusion of that, the structural model cannot only predict the backbone structure, and there are three typically in the quaternion parameterization of the translation, which is like the translation distance and also their rotation. The general input and output will be pairwise information that are determining the configured matrix of each residual toward other residuals in the same proteins, as well as the target MSA, the single representation of R and C. So this is one row from the MSA matrix, and that is the pairwise matrix. And also the starting input for the backbone. The backbone is generally parameterized as the number of residual. 3 by 3 is the general matrix transformation, and also R by 3 is the translation parameterization. So the general module here is the 8 blocks shared weight module for the positioning update, and also the output would be either from the main side is the main chain, the backbone frames, as well as all the atoms angles. So those are producing or compute all the atom positions. In terms of evaluating the distance, there are multiple ways, as we mentioned before. So there's one specific measurement will be on all atom position, and another relatively easier evaluation will be only on the backbones, which is the alpha carbon of in the proteins. In general, in terms of the module, it follows the very complex architecture as well. And it's from the input, as you can see, the pairwise matrix and the single row of single row of residual, which is the target protein we want to predict. And also we are updating the backbone frames as you can consider the backbone frames is the general global coordinate parameters. And in terms of the input, relatively it's really, I think it's really a complex architecture here. So generally, the architecture can be composed into 3 parts: the bias and it being transformed into the H parameter, and here is the bias matrix, and will be later in input as one of the 3 components before the softmax. And in terms of the middle part, following the structure, it forms a single row of single representation, 1 row of residuals to a dot product, product's affinities. It has a shape of R by H. We have seen that kind of similar structure before by the key and queries. And also there will be some specially designed for specific to combine with their backbones coordinates. So in that case, those are square distance affinities are being generated through another channel of mechanism, attention mechanism, query value and products, and being concatenated with the current global frames of backbones. There is relatively some theoretical analysis on the L2 norm and affinities are being robust to invariant to the Euclidean transformations. So they can use that for so they're using a notation of local frames and global frame in terms of navigating and localization of the backbone and also the side atoms. And afterwards, going after the softmax are going through 3 other different attention weights and being concatenated with the pair and single row column, and also with the global frame values, and being outputted to the final updates of the same row. And this kind of 1 block are repeated 8 times, and then going towards the final representation. And using that representation in the meantime, they can still output based on the representation. They are still outputting the prediction of the backbone as well as all the atoms in the side chain. I would say there will be specialized design also in the training. The trainings, I'll point out some important or some I believe is transferable setting for other kind of task. So the first one, as I mentioned before, is called self-distinction, which is actually a 2-stage design in terms of fully structured or fully known protein structures, as well as the main part, which where we only know the protein sequences, but not the protein structures. So there are cases that first train the base model using the information of PDB protein knowledge base, where we do have the information of both sequences and protein structures, and to use that to train a base model and predict on the rest of the unique cluster sequences to generate an initial round of protein structure prediction. Inside the model, they also have a intermediate result on protein residual level confidence for a protein. So you will roughly know whether this protein structure, although you don't have the ground truth information, but you can output a score with a certain confidence whether this protein are good enough, or by the model itself are good enough or of high confidence. If part of them are confidence, they have a certain strategy to or threshold to select the high confidence part and put that as part of this, treated as almost a ground truth, together with the PDB real ground truth, and to train a full model. And the full model are being like a quarter of them are from the PDB structures, and 3/4 of them are from the actually without ground truth but confident predictions. And then we'll get updated predictions on the context proteins. So there is a context and to evaluate your final result to be compared with others. So this is they call the structure.
Question here.
Go ahead.
So you said 25% from the PDB, right? Which is known structure, and 75% from this new uniclass, right? These are predicted ones, right? Mm-hmm. My question is that how do they make sure that there was no bias introduced by this 75%? I mean, more systematic bias.
So I would say, personally, I'm not sure about how to identify the bias, but one thing I read from their technical report is the 75% is regarding the number of towards the PDB part. So the 75 are sampled every time they're sampling from a different portion of the uniclass prediction, highly confident predictions. So the 75% is not static, so they are dynamically changed, but 25% are actually will be static and the same and be input into training all the time.
Yeah, but if there's a systematic bias in uniclass, because they may use the same prediction model to predict everything, right? There may be some systematic bias, but that doesn't get resolved by taking different random samples.
Yeah, I believe the case you mentioned would be a potential risk for any. You can imagine they are claiming they can utilize some the information from the structures from the proteins without a known structure by this kind of technique. But I definitely believe there will be potential risks to use that. So in terms of I didn't see any analysis on identifying potential biases, but I will show some of the critics by other group or by other researchers outside of DeepMind on their observations or on their trial of the DeepMind's demo on certain type of proteins.
Okay.
I will point out those slides in very soon. So they're in some future slides. And in terms of other losses, so definitely there, if you remember last time we have like global distance test, we have our RD and B, which is roughly a Euclidean root square distance of all the atoms in terms of their localization. So in terms of losses, they have a lot of losses and also auxiliary losses for better performance. So I have several. So first, their main loss this is called frame adjusted position error, or I think that's some error. They are trying to identifying the distance between the ground truth and the predictions in the local frames instead of being treated in entire global frames. They're using this kind of loss as their primary training loss as well as others. So there are some other AUX and distance loss. And in terms of MSA loss, they are more like in the fine tuning stage. Sorry, not fine tuning stage. In terms of self supervision style thing to do average cross entropy loss to max the MSA prediction. If you still remember, the MSA representation are being updated extensively during the entire model. So they use the MSA loss to that also they have some mask values in their MSA representations, and they want to use the update representations to predict that and recover that mask. So this kind of similar to what we have in BERT. And the other part of loss called model confidence prediction. So this is from another kind of evaluation where they have certain evaluation score of per residual. So they have a per residual score in terms of their distance or closeness. They are putting into the distance level in per residual by their the alpha carbon atoms. So which means they use a series of combinations of losses together. If you see the rest of them, there are some experiment resolved and some violations. So they are specifically designed by the biochemistry scientists in DeepMind, and especially for the violation one, they have identified several rules or several potential identification on the structural violations. So they will put that into the fine-tuning stage where they want to mitigate the potential large error, especially occurred into some known biochemical knowledge, and they are trying to mitigate this and let the model aware of such violation could have a huge cost. I personally don't have the knowledge on explaining the violations potentially, but just point out it would be a huge, massive engineering work to design what are the effective losses, and together with their training strategy. They have tested some ablation study on removing certain part of the model, either self-distinction training or some extra MSA or some other resources. And they are showing the best performance as their report as the DeepMind's most advanced results. Just a quick demo about what their protein database here. It's pretty cool, and in terms of their prediction. And if you remember the residual-wise confidence, so this is about their model confidence output. They have a certain part of the module to predict how much confidence you have for each residual. So in terms of they report most of the main part. I would say I cannot identify whether their main part or some tailing or heading, especially to of the protein, are very likely to be not so accurate. But in terms of the A helix and the beta sheet are doing pretty good. And the one I have here is more like this is called ACE2 protein, and also being verified experimentally. And they are together with you can see from the sponsor, yeah, they are together with the YAMBL-EBI, which is the, I think I have heard that name before, binded with their protein database. And this one is a role that AI played in prediction. And also they will have some prediction aligned error, and you can see the general main part, the green part will be, position error will be very less. The dark green means good, and the light green, as you can see from the tailing part, which is more like the boundary of this configuration matrix, are relatively in a lower accuracy. And if you're interested in any kind of the reproduction work, then you can check about, I provide all the link of the source code and as well as the Google Colab link. For Google Colab, it can be very easily overflowed about their default setting in terms of model usage, but you can still run a little bit about how their the model are being input into inference. And in terms of source code, even though they provide very much detail about the reproduction, but in terms of the data size and the computation resources needed, it might not be an easy work to reproduce in an academia setting. I personally say that. And in terms of some quick conclusion or takeaway message about AlphaForward, first, there is no doubt that superb engineering is involved, and there will be innumerable combination and trial and error process to find the best modeling, empirical modeling. And also the computation power is needed, but not that much as some most state-of-art language model. Their claim they're using about a power of 128 TPUs. It might be beyond the capacity of in the academia setting, but it is not a huge amount for in the corporate setting in terms of computation power. But finding the best combination and resource together is not just a simple brutal computation power, but also a lot of design in terms of modeling. Some limitations I will point out. First thing, there is a lot of why so questions for every module of design. So why they are designed this way? They are not giving a specific explanation of why, because that's the empirical best result, and they're saying they're using this kind of architecture. And from their technical report, we cannot find DeepMind has discovered any powerful insight about protein structures, or they are specifically specific discovered by AI or anything about knowing more about the structures. They are pretty much still a predicting tool. And in terms of accuracy, as I mentioned, it's just about 80%. And in terms of putting into real production in pharmaceutical industry, this is I think it's relatively very much below the standard of that. And in terms of some case study on whether it is okay to use, some other researchers external from DeepMind are testing or checking a couple of examples on specific type of proteins. And DeepMind technical papers claims that the MSA as part of the input, they do heavily rely on a large amount of similar sequences in the MSA table. If the alignment or MSA is less than 30 sequences, the performance can drop dramatically. So it relies on certain part of support of known templates and MSA for their modeling. Researchers found specifically check on proteins, people very interested in short human design proteins, and also others are antibody proteins. But this is just a observation, but probably not systematically tested on all human design proteins or antibody proteins. But generally, they are saying relatively it is working okay for general structures on human designed short there's a typo, short proteins, which means very likely for human design proteins, it has a relatively shorter sequences, because they are relatively, for engineering side, it's relatively difficult to design very long proteins with the specific functionality. For antibody proteins, they're reporting inferior performance on the antibody type of proteins, so based on some specific protein groups. I'm not sure whether that is related to what Wei has suggested, whether they are good, super good or super bad on specific proteins as part of their potential inductive bias in terms of the self-discerning training, or it's relatively difficult to identify where the problem is if we observe certain inferior performance due to their large and complicated design for AlphaFold. And definitely it will be beneficial as an inspiring work to biology and structural bioinformatics. And even as a very special model of DeepMind itself, it's relatively incident for academia and industrial research in terms of their gaps and differences. If you're interested in, there are other works related to protein folding, and I didn't notice there are technical report, but only a science paper by University of Oxford and University of Washington. They are designing a pretty similar, not similar, but still for protein folding problem with 1D tracks, 2D track, and 3D track, with the usage of, they call it SE3 transformer, which is generally a graph neural network structure for a roto translation invariant graph neural network structure. So because we haven't got the specific detail or very large technical report for this paper, this is a general guideline for their paper, which is called Rosetta Fold. The performance is still lower than DeepMind's AlphaFold, but it's still comparable and exciting results. And also the Rosetta Fold is public available in terms of their code reproducibility. And if you're interested in the SE3 transformers, or later we are interested in how they're modeling the graph or point cloud in a transformation invariance model, then you probably can check this paper about their 3D block component. That's pretty much the part I want to share about the story of AlphaFold. I understand it's pretty much out of the domain or general domain of our the research in our lab, but I want to point out several things that could be a little bit transferable to other models, including their attention design, their formulation of residual graph in terms of their a complete graph in terms of modeling residual in a confusion matrix manner, and also some training strategy in terms of self-distillation and utilize a large amount of unlabeled data to improve the performance, but definitely with certain risk in terms of the this kind of training strategy. And again, if you're interested in more resources and blog and post, or even some videos, and feel free to check this video I sent out last time after the seminar about this Google Doc, and you can check about, especially one most well-written resource will be OpenFold, which is a project that are integrating multiple model structure, GPT SE3 transformer, and some a lot of toy examples and data set you can check. Yeah, that's the end of my presentation, my reading group seminar, and feel free to check out the resources I've listed here. If there's no questions, I'll probably hand over to Derek.
Should I start now, or?
Yes, please.
Okay. Let me share. Go back. Okay. I guess we'll just get started. So the title of this paper that we're presenting is How Neural Networks Extrapolate from Feedforward to Graph Neural Networks. The authors are from MIT, University of Maryland, University of Washington, and National Institute of Informatics. The general idea of the paper is analyzing what happens when your testing data set is very different from your training data set. And I think this is very relevant to our research in that it kind of points out some critical flaws with feedforward or multi-layer perceptrons, and how graph neural networks kind of fixes those flaws to some extent. And lastly, I want to mention that this paper was published in ICLR this year, and it received one of, if not the highest score at the conference of 9, 9, 9, and 8. Yeah, so I guess I'll get started. So high level, what is the question they're asking? They're asking, can neural networks extrapolate to testing data that's outside of the training data? So for instance, if you're in some high dimensional space and you have these star points, which are testing data, and these circle points, which are training data, they're asking that, okay, so if your testing data kind of comes from a bigger region of this input space than your training data does, what happens when you run a trained neural network on these testing data pairs, right? And for graph neural networks, it also kind of have implications for when you train on kind of small graphs and test on big graphs, or if the embeddings of your training training data set is very different from the embedding of your testing data set. What does this kind of do? And does this kind of introduce any problems? Before going into any of the math, I just want to directly give you the answer. So there's two key results. The first one is that if your testing data set and training data set is different, then your multi-layer perceptrons can only learn linear-ish kind of functions. This is very counterintuitive because we were always told that like neural networks are universal approximators. They can learn like any nonlinear kind of function, but in their kind of setting where your testing data set and your training data set are very different, it can only learn kind of linear-ish functions. The second question is, what about for graph neural networks? And their answer is you can extrapolate very well if all your nonlinearities are incorporated in your aggregation function. So for their graph neural networks, they adopt like the message passing kind of framework. So they're saying you're like doing an MLP, you're aggregating from your neighbors, you're doing another MLP, aggregating from your neighbors. So if you let all the MLPs be linear functions and encode all of your nonlinearities in these aggregation steps, then you're able to perform well on testing data that you don't see in your training data. So these are kind of broad. So and to build up to these two kind of key results, the paper is kind of dense in that it goes through multiple kind of steps. So I separated the paper into kind of 4 parts. The first part is saying that MLPs failed to extrapolate to nonlinear functions. So we're going to prove that for testing data that's very, very far away from training data, that your functions basically all become linear. The second thing is they're going to prove when multi-layer perceptrons extrapolate is if your ground truth function is linear and your training data satisfies some certain properties. So then they give you a condition where MLPs actually do extrapolate well. Next, they're going to give a hypothesis for GNNs, which is basically saying that if we encode all the nonlinearities into the aggregation step, then our GNNs should be able to extrapolate well. The reason why they name it as a hypothesis is they don't like formally prove this, but they give some pretty convincing experiments about this. And the last thing is some case studies. Specifically, they do prove that for the task where you're trying to find the minimum or maximum degree of a graph, that you can train a GNN with certain aggregation functions that can perfectly extrapolate to all testing data, given that your training data fits some sort of like conditions. Is there any questions on the overall summary or high-level ideas?
Yeah, I have a question. So for GNN extrapolation, we mentioned that the test data has the different distributions and training data. So my question is that because GNN needs to collect information from neighbors, right? So are you saying that when we are applying GNN on the test data, all the neighbors are also like from the test distribution, or only the test node is from test distribution, the neighbors can from the training data?
I see. So I think some solid example might help. So in the GNN kind of experiments, your test data will all be from a certain distribution of graphs, for instance, like Albert, Erdos Renyi, and a bunch of like these random graphs. But they fix your training distribution to, for instance, only be complete graphs, or your training distribution is only like graphs with certain density, or your training distribution, yeah, like that.
So you are sort of saying that so it's the training test and the training data and test data, they are like disconnected graphs. It's not like adding a few new nodes to the training graph, right?
Yeah, I think it's more graph level, depending on the task. Yeah.
I see. Okay.
Any other questions? Okay, if not, I'll continue. So before getting into like this kind of story, they also require like quite a lot of kind of background. So the first kind of question is, well, we're talking about multi-layer perceptron, but what really is a multi-layer perceptron? So what they kind of operate on is what's called a neurotangent kernel, which is when you take the width of your neural network here, and you set this width equal to like infinity. And then you also take your learning rate and you turn your learning rate to basically 0. And when you do this, you get these very nice properties in that your trained neural network, so your weights at time infinity, kind of turns into a kernel regression solution where your kernel is a deterministic kind of Gaussian process. And another property is that you can, with like some very kind of loose kind of constraints, you can show that the training loss can equal to 0 in this case. So we'll go a bit more into this so that it's not like too weird, but yeah, this is also one of the major kind of criticisms of the paper, because they say, well, you're only operating in this NTK regime and not like any like MLP regime. But I guess the argument against it is saying, well, if you have an infinitely large neural network and you can't learn your function, then how can you expect your smaller neural network to? Okay. So I'm going to do a bit of math, but I think this stuff gets like kind of really deep. So if people have like better intuition or better understanding than me on this part, like feel free to interrupt. So the first thing we're going to do is define our MLP. So we basically have these three kind of equations to define it. So our input kind of layer here is just going to be our input X. Each layer is the activation of this alpha tilde. And alpha tilde is equal to our standard kind of like weight plus bias. We also have this extra like scaling factor here, because if we're taking the weights and like scaling them up to infinity, you need this extra term here so that you don't kind of blow up all of your activations. So given this, we can look at a particular neuron in this neural network and see if we can make any conclusions when we take the width limit, right? So if we look at this, the second or the ith neuron of the second layer, we can write it out as like 1 over root n and then like copy over the equation. And what we notice is if we take this limit n1 to infinity, that this first part kind of becomes a Gaussian. The second part also kind of becomes a Gaussian by the central limit theorem. And this is kind of a really key result, and also kind of relies on the fact that you initialize your like variables with Gaussian distributions. But once you do this, you can kind of see that the expected value of this alpha tilde is equal to 0, because W is 0 mean, and this B is also 0 mean. And from there, you can, oh, this should be alpha tilde, but you can kind of conclude that this entire neural network kind of turns into a Gaussian process. And I think Sichang gave a presentation on Gaussian processes in the past, but basically what it is you can take like your covariance matrix over all of your kind of data points. And then from that, you can kind of do predictions and stuff with it. So this is kind of the key conclusion in that you can recursively kind of write these covariance matrices, and that by law of strong number, you can also make it so that all these covariance matrices like go into like this deterministic kind of values. And from here, we kind of reach this conclusion, which is that if we make the width of our neural network approach infinity, then the untrained multilayer perceptron becomes a Gaussian process. So this is all fine, but there's a question here, which is what if we make this untrained MLP into trained, right? So
Eric, I have a question. That this is a very interesting idea. So when you say the untrained MLP becomes a Gaussian process, are you talking about the output?
yeah, so it's kind of tricky. It's saying the output of each kind of neuron, given the incoming neurons, is a Gaussian process, if that makes sense. So strictly speaking, this should be like alpha tilde of L given alpha tilde of L minus 1. That is a Gaussian process. Yeah.
Condition on the previous output and the output of the current layer becomes a Gaussian process.
Exactly, yeah.
Then how the covariance matrix, you talked about the mean of the Gaussian process is 0. Then how about the covariance matrix? Is that a function of the previous input?
Exactly, yeah. So if we look at the first layer, it's simply equal to like the input x, and then it's like x transpose with x prime, and then plus this kind of bias term here. If we look at the like next layer, we kind of get this recursive definition, which is 1 over NL, and then like the dot product between the two previous activations plus this gamma squared term. And then by the law of big numbers, I think if you tend this NL towards infinity, this turns into the expected value of kind of the previous outputted Gaussian process plus this gamma term. So you basically have your input x, you feed that to a Gaussian process to get your first layer. You take the first layer, you feed that into a Gaussian process to get your second layer, and then recursively, so forth.
I see. So during all the process, do we need to make any assumptions to the, for example, the distribution of Wij and the distribution of Bi?
Yeah, so I think the main assumptions here is that you're taking the limit like 1 by 1. So you're taking the limit of alpha 1 to infinity, and then you take the limit of alpha 2 to infinity, and then limit of alpha L like to infinity. But I think like recently and like the past couple of years, there's been like papers proving that you can take the limit all at the same time, or you can like find like a bound, like the weakest definition of limit or something like that. But yeah, does that answer?
Yeah, my question, like, in order to prove things here, do we need to make assumptions on the distribution of the initial input x and the parameters on the MLP, including W and B? Do we need to make any assumptions?
Yes, so I think the assumption is W and B are initialized as Gaussians.
I see. Okay.
Yeah.
How about X?
I don't recall there being any like things on X.
Okay. And it's not learnable, right? Because learning rate is 0.
Yeah, since it's the untrained version so far. That's clear. We can. Were there any other questions? Okay, I'll move on to the next one. So we know for untrained networks, it's like a Gaussian process, but then what about trained networks? For this, there's kind of this empirical kind of finding called lazy training, which is that if you make your network width approach infinity, then the kind of change in your weight approaches 0. So this is the intuitive kind of explanation of this is once you have like so many like parameters, you only need to move each parameter by a tiny amount to get you to where you want to be. There's also some proofs for this as well, but I think it was like a bit too advanced for me. So I kind of went with, I mean, we also know like empirically, this is something that happens. But once we know that this happens or accept it, there's this very interesting thing that we can do, which is say that the derivative of your output with respect to your weights is approximately constant because your weights don't change much. And once we know this, we can use the Taylor series to approximate what the output of our neural network is. In other words, the output of the neural network is with theta at time equal to 0 plus the derivative of theta times like this difference here. And this is very interesting because we can see that this first term, we can just let that equal to 0. We can say that second term and just say it's some constant beta. And now we instantly have arrived at a formula that tells us what the output of the neural network is once you've fully trained your kind of network. And this is equal to the gradient of your f with respect to your parameters multiplied by some learnable beta matrix. So specifically, we've converted this very complicated neural network into just a linear regression kind of problem with this 5-feature map that maps to an infinite number of derivatives with respect to your weights. So we can write this out as an optimization problem. And then if we take the solution, we can use like the kernel trick and write out the kernel solution kind of here. So basically what you do is define a kernel as the dot product between your gradients of x and x prime. And then you, to make a prediction on a new data point, you simply take like the kernel of your new data point with all your training data points, project that into like the space, and then you take the inverse training matrix to project it back to your original space, and you take like a summation of your y training points based on this kind of kernel. And so for the paper, this part isn't that important, but you can also show that the NTK is a deterministic kind of kernel that you can physically compute. And similar to our previous step, when we do this, it kind of all becomes a very big Gaussian kind of process. And then the whole conclusion here is if we let the width of a neural network approach infinity, then the trained multilayer perceptron approaches the kernel regression solution, where the kernel is this neurotangent kernel. And because this neurotangent kernel is kind of fixed and unmoving, because these derivatives is also approximately kind of constant, then this entire thing kind of works here. Any questions? Okay, yeah, so this is the first major conclusion, which is that you can write it out as this kernel solution that we're going to use later. The second solution is what happens to the training loss? And can we say any dynamics about our kind of neural network once we take those two assumptions? The first thing, we can simply look at gradient descent. So gradient descent is theta of t plus 1 is theta of t minus some learning rate times our gradient of our loss. But we want it so that the learning rate approaches 0. So then our whole kind of discrete process turns into a continuous process. And this kind of, we want to kind of rewrite our the change in our learning rate as a differential equation. So what we do is we say d theta dt is equal to the limit of the change in our weights over the learning rate. And we can simply plug in what t plus 1 equals to here. And you can see that this data and this data cancel out. This learning rate and this learning rate cancels out. So then what you end up with is that the change in your parameters is equal to the negative gradient of your loss. And for the mean squared error case, we can write out what this gradient is equal to, which is just the summation of kind of like the difference multiplied by df d theta. Okay, this is great. So we know the dynamics of our kind of parameters, but can we know anything about the dynamics of the output of the function, right? So from this, we can simply do chain rule, which is that df dt is d theta of t times, this should be df d theta. Yeah, so sorry, this one is df d theta, but we can expand this d theta dt with our solution here and plug it here. And this one is still df d theta. And then we can kind of say, okay, this is the inner product of this sum. So we could take this sum out and turn it into the sum of these inner products. And then here, there's a very kind of clever trick that we notice, which is that this term here is exactly the neurotangent kernel between xi and x. So then for the training loss, we can simply write it as df d theta is this kernel, this deterministic kernel, multiplied by this kind of difference. And then from here, we can solve this differential equation like this. So now let's define a new term u, which is the difference between our neural network output and the ground truth. And what we see is that it's equal to, like at the 0th iteration, what the difference is, multiplied by e to the negative neurotangent kernel times t. And from here, we know that since our model is overparameterized, because we have infinite kind of weights, then the neurotangent kernel is likely positive definite. So that means this first term here most likely tends to 0, which implies what we wanted to find, which is that we can achieve 0 loss on our training data set. Yeah, so any questions up there? I think that's all the kind of background.
I try to understand the motivation. So for the first part, we want to understand the dynamics of the theta t, which is like how the parameter is changing along the training process, right?
Mm-hmm.
Then why do we interest in the second question?
Yeah, so I think all three of these questions kind of lead to this final conclusion here. So all we're trying to say is that the loss approaches 0. And to get the loss approaches 0, we kind of want to write some dynamical equation of the difference between our true ground truth training pairs and the outputted predictions. So to get this, we need the kind of differential equation of f with respect to t. And to get the f with respect to t, we need this d theta dt.
So we want to know that the training loss approach to 0.
Yeah.
Yeah, I think this is very related to what Professor Junheng Hao is doing.
Yeah.
He also has proved that for a very wide MLP, actually can guarantee that the training loss is going to be 0.
Yeah. I think some of this is like kind of like took from the course he kind of taught a couple quarters ago.
I see. Okay.
Yeah. So from here, I guess now we have all of the kind of background, and these two things are a lot more clear to us, which is that at the infinite amount of time, the output of our neural network is this kernel solution, where the kernel is a Gaussian process, and that the loss is equal to 0. Another kind of 3 assumptions that the authors of the paper make, in addition to NTK, is that the activations are all going to be ReLU activations, that the number of layers is going to be equal to 2, and that the loss is mean squared error. And this was actually like brought up in the kind of like rebuttal kind of process. And reviewers were kind of concerned, well, if we don't have these assumptions, does it still work? So they provide some experiments for non-ReLU activation. They say that the proof can easily be extended for more layers, but it's just like kind of difficult. And for loss, they leave it as future work.
I just want to double confirm for the NTK, what is the input?
Yeah, so the NTK is kind of a deterministic kind of function that takes in two inputs, which are 2x kind of 2x
see.
input data points. Yeah, and then outputs some value. Cool.
Okay, thank you.
Okay, so from there, we can finally go to the first theorem. So the first theorem is basically saying, suppose we train this 2-layer ReLU MLP with square loss, where the MLP is really a neurotangent kernel. Then for any direction V, where V is kind of your input, we can let X naught equal to TV. So we want to push X naught outside of your training distribution. So we're going to let T approach infinity. Then we will say, if you have a little bit more than TV, so TV plus HV minus F of TV is equal to beta V times H. So I think this graphical picture here would make more sense. You have your input data point X naught, which is like here, and you want to push it outside of your training distribution. So you're going to make this T very, very big. And now you want to prove that once this T is very big, that your functions kind of just become linear. So then it's saying, okay, so then if you add a little bit more than T, like T plus H, then your Y value is going to increase by this linear term of H times beta V, where beta V is some vector and H is some scalar. Yeah, and they give this convergence kind of like bound, but we're not going to worry about that for now. Any questions on the overall kind of idea here? It's just saying, if you're very far away from your training data set, then everything becomes linear. Okay. If that's the case, we can roughly go through the proof. Basically, what they do is, if we recall, we're learning beta transpose phi of x, where phi is equal to the gradient of f with respect to your weights. So in their proof, what they do is analyze what this feature map is equal to. And what they write is that it's equal to x times this indicator function and w transpose x times this indicator function, and then all of this towards infinity. So then the question is, well, what is this WK? Well, this WK is, if you look at like a section of your neural network, which is W times X, this WK is simply like a single row in this giant WL matrix. So then how do they get this value? Well, they just take the chain rule, and you can realize that, well, one part of it is kind of this indicator function. Another part of it is either this X or this W transpose X. And then this first part, I think because they're like the 2-layer case, like you don't really need to worry about it, but we'll just put it as C prime here. So each one of these entries is kind of describing one row in the giant kind of weight matrix. Okay. And once we get this thing, the rest is kind of all just algebra. So we consider our x naught, which is TV. We consider x, which is x naught plus HV. And for ease of notation, they also call this 1 plus gamma of x naught. And we're going to take t to approach infinity. And notice we kind of skipped the bias in the top part. And the way they account for that is they say we let x hat equal to x at 1. So then whatever weight is multiplied by this 1 is kind of the bias. Once they do that, then you can write what f of x hat minus f of x naught hat is equal to. And that's simply equal to the beta from your NTK plus this phi of x, where your phi of x is the phi of this one minus the phi of this one. So as you can see, it's like this x minus this x naught, this w transpose x minus this w transpose x naught, where each one of these terms is just the same as this top term here. And from here, they do a small lemma. So they look at a single instance here. So they say, what is xi minus x naught I. They say xi minus x naught I is xi of this plus this term minus this term. And the reason why they're trying to add this term is that they want to turn this x naught here into an x minus x naught. So by rearranging this extra term that you added, you can rewrite this x of I of w transpose x greater or equal to 0 minus x naught of I w transpose x is greater or equal to 0 as x of I w transpose x greater or equal to 0 and so on.
Yeah, Derek, I still have a question. Like, what's the indicator functions? Why, like, when we try to write down the derivatives, we encounter this indicator functions.
So this is from the ReLU. So ReLU is equal to, like, this thing is 1 if it's, yeah. I think, like, just taking a step back, the whole proof is basically saying as you go really far away from your training distribution, then all of the ReLUs that are subtracting each other, which gives you nonlinearity, all disappear. And all you're left with are the ReLUs that are like activated. And the sum of all activated ReLUs is basically just a like linear function, which is why they're kind of setting this up as this I of W transpose X naught and this I minus I, because this first term is what's going to give you your nonlinearities. And the second term is what's going to stay once you take the limit. Yeah, and they do the same kind of algebraic manipulation for the second term of right here. Yeah, and doing all this algebra, you can plug all of this into here and then divide everything by h. And what you get is this set of equations here, which is the sum of all beta w times this, which is, I believe this is x. Let me check. Yeah, it's x. So this one is x hat with this thing here. This one, I believe, is also x because x is 8 or x naught, which is hv. And since you divide by this h, it's only v now. And similarly, you get this big equation here and this big equation here. And then from here, we can label each one of these terms as 1 or 2. And we can look, check out the indicators for all of the ones that are labeled 1. And what we see is if we let t approach infinity, then W transpose of TV concatenated with 1 is greater than or equal to 0. In other words, W transpose of V is greater than or equal to 0, which means this is simply this indicator here. And the second term, which is responsible for our nonlinearities, we can rewrite it as this W transpose 1 plus gamma of this x naught, or 1 plus lambda of x naught, and W transpose x naught here. And as you take t to infinity, this lambda approaches to 0. So what you get is this indicator minus the exact same indicator here. So then this approaches 0. So high level, what is going on here? It's saying that all of these kind of ReLUs that subtract with each other, they all kind of disappear once you're very far away from your training data set. And all of these ReLUs that are not subtracting to each other, or are basically just linear kind of ReLU functions, all of these kind of remain. So then the only terms you remain with is these beta W linear terms. In other words, in this big equation up here, all your 2's are gone, and you're only left with your 1. And that's why as you go very far away from your training data set, everything becomes linear. Yeah, so that's the proof. Any questions? Okay, I guess the next thing then, now we know that very far away from the training data set, everything is just linear. So then the authors ask, well, can we perfectly learn a linear kind of ground truth function given a training data set? And here the argument is you can only do so if your training data set kind of spans the whole space of your input X pairs. So if your input is in D-dimensional space, then your training data set has to contain an orthogonal basis that spans that entire space and also the negative version of that orthogonal basis. Is there any questions here? I think this point isn't as important as the previous one, but it's still a pretty major conclusion that they make. Okay. So for the proof, I'll go over it a bit more quickly. So what they basically do is your ground truth function is this beta G transpose X, and you're learning this NTK function, which is beta transpose this kind of feature map of X. And we've previously defined what this feature map is equal to. And from here, we can group all the beta NTK terms that point in the same direction by this and this. The reason why we have two is because one of these has this extra WK term here that we include here. And then from here, we can rewrite the entire equation as a constraint optimization problem. And we can move this beta G into here to turn it into a form that we can use Lagrange multipliers on. And then they gave a very long proof on Lagrange multipliers, but the ultimate conclusion is this beta W plus beta W prime W is equal to 2 beta G. And from here, if we rewrite the NTK function and substitute in the Lagrange multiplier, what we find out is that we get our original function. So yeah, that's the proof. Since it's not that important, I think this is just general outline. Yeah, so I think the major conclusions are that we know for interpolations, MLPs can learn any kind of nonlinear functions. But for extrapolation, MLPs can only learn linear functions when it's very far away from the training data set. And this kind of implies that MLPs are kind of not that good, because if they can only learn linear functions, then we can't really solve this extrapolation problem, right? And the key takeaway here is if you're only using these deep neural networks, is that data is super important, right? In other words, if we start encountering test pairs that are very far away from our training pairs, then the entire model kind of just breaks down.
Here I want to make some comment. I think this line, following NTK, this line of research is people still have lots of debate of this because it really requires lots of assumptions.
Mm-hmm.
For example, it has to be very wide, right? The number of neurons each layer has to go to infinity, which in practice we're not really doing that. Mm-hmm. So yeah, my comment is very related to whether this conclusion can be generalized to general MLP. It's still debatable.
Mm-hmm. Yeah, I think that's very true. I think in this paper, they give some more experiments on if the activations are say non-ReLU, but all of the experiments are kind of still under this NTK kind of assumption. But yeah, I guess if needed, we could also try experimenting ourselves with just neural networks that aren't that large and seeing if the same results hold.
Then when they do the simulation, how wide is their neural network?
Oh, I think I need to double check on that one. Maybe I can follow up through email.
Okay, that's good.
Yeah. Yeah. So these are the general conclusions on MLP, and they also provide experiments on non-ReLU MLPs and come to a little bit different, but similar conclusions. Basically, if you're cosine activation, then as t approaches infinity, then what you end up learning are all cosines and not tan H's or quadratic equations. But for us, what's important is like this GNNs. So what they propose is kind of this hypothesis of linear algorithmic alignment. And what they're basically claiming is if you have a ground truth function that you're learning, which is equivalent to a graph neural network, except in each of the projection steps, it's a linear kind of function, then you can train your graph neural network on a subset of the data to perfectly learn what you want to find. So in this example, you have the shortest path algorithm, which you can write it as dynamic programming here, where you have this minimum function here, you have some linear function here. So then you can rewrite this as a GNN, where the aggregation is the same as the dynamic programming aggregation. You don't know what this linear function is, so we replace it with a multi-layer perceptron. And then their argument is, if your training data set is diverse enough, then training this neural network will give you the exact output as the shortest path. And for instance, if you change this min v into this summation, then you won't be able to perfectly learn the shortest path. And the reason here is because if you have summation here, then all of this min non-linearity has to be learned in this MLP kind of portion. And we already know for MLPs, as we approach infinity, they all turn into linear things. So then this whole thing becomes linear as you approach like infinity. Is this argument kind of clear?
Yes,
think
it's clear to me. But
Okay.
Yeah, from why we need this mean self summation is quite clear to me. But then
Yeah.
how we can guarantee that using this messy passing framework to solve the shortest path problem, can you also elaborate that part?
Yeah, so if this MLP function learns this function here, specifically if the output of the MLP turns into h of vk minus 1 plus w of vu, then this bottom function is the exact same as this top function.
So are you saying that then this hvk minus 1, this latent representation, if somehow it directly reflect the value of the dk minus 1b, then we should be good.
Exactly, yeah.
Okay. And in the shortest path, that's going to be a scalar, right?
Mhm.
Okay, for this shortest path is because there are like different shortest paths problem, this is like fixed source or something.
Yeah, I think so.
Okay.
Yeah.
And do I need to specify the number of dimensionality of h as 1?
I think you can specify anything, because even if you specify dimension as 100, the MLP could set like the 99 dimensions to 0 and only use like one of them. Yeah.
Makes sense.
Cool. And they kind of verify this with experiments as well. So they use both min-max pooling and sum pooling. And for shortest path, you can see with sum pooling, the extrapolation error is a lot higher than interpolation error. And with min-max pooling, your interpolation and extrapolation error are both 0. And all of these error, I think, are mean absolute percentage error. So you can see here, this is better. They also tried training with different training graphs, so like path, tree, cycle, ladder, for all of these different training paths. They all test on what they call general, which is a collection of random graphs with random kind of densities from the network X package. So then here you can see with certain types of graphs in the training data set, it actually doesn't learn that well, but if you have good kind of training data set, then it learns well. And also they show that with very low density training graphs or very high density training graphs, you also don't learn the ground truth function. Only with this kind of not too high, not too low density, you learn the correct function. the next thing is they kind of prove this theorem here, which is saying that if you want to find the maximum degree in a graph, then if this function here, like the maximum degree of g's and minimum degree of g's times ni max times the maximum degree, ni min times the minimum degree, all this, if your training data set spans this space, then you perfectly learn your max min degree function. So when does it not span this space? Well, it fails if all the training graphs have the same degree nodes. So for example, if you have path graphs, if you have k regular graphs, if you have cycle graphs or ladder graphs, then all of the degree distribution or all the degrees are the same. So you don't span this kind of space. So then when they run experiments, you can see the extrapolation error for the cycle, ladder, and for regular and path graphs are like kind of very bad. Whereas the expander, complete tree, and general graphs are very good at learning this task of finding the maximum degree in a given graph. And they also mathematically prove this theorem here using kind of the exact same technique as lemma 1, where they use the graph neurotangent kernel instead of the MLP neurotangent kernel. Yeah, is this clear? Cool. Lastly, they give an example of when GNNs fail at extrapolation. So they consider this kind of physics problem where you have a bunch of kind of planets, and these planets are all moving. And the goal is to predict the velocity of the planets at like all different points in time. And the reason why GNNs kind of fail here is because your acceleration is kind of a non-linear function. Like the aggregation here is sum, but it's summing over non-linear kind of functions on the input kind of features, right? So then that means even if we're able to get low interpolation error, we're going to get high extrapolation error because the MLP parts of the GNN will all converge to linear functions. So then their solution is considering two types of features. One type of feature, okay, so both types of features all use the same node feature, which is the mass, position, and velocity, but the edge features are different. So for one case, they set the edge feature equal to this inner kind of non-linearity portion. And for the other case, they set the edge feature equal to 0. And as you can see, if you use the original feature, even if you're able to achieve low interpolation error, it's going to have high extrapolation error. And with the improved features, you can get both low interpolation and extrapolation errors. Yeah, and yeah, so all of this goes back to our two key takeaways. The first one is MLPs don't really work when test data and trained data is different because they all turn linear. And the other one is to have GNNs work provably for extrapolation, you need to encode all the non-linearities in the kind of aggregation step and let the projection steps all be kind of linear. Yeah, so that's kind of the presentation. And if there's any questions, I'm happy to take.
Can you go to the previous slide?
Yeah.
Because this one is very related to the GS research, which is on the dynamic system. I just wonder, for example, for the first formula, right, so on the right hand side, it looks like we try to model the trajectory along with the time t, but on the left hand side, this FGU does not really contain this time. I just wonder like how they wanted to utilize this graph neural network to model the dynamics.
Oh, are you talking about this top one here?
Yeah, the top one.
I think this is kind of the ground truth, like physics equations that govern what X and V are at every iteration in time. And I think there's so.
Yeah, for example, yeah, so
exact...
usually we are given by those differential equation.
Mm-hmm.
For example, let me see which one is differential equation. So, okay, I can only see like equation 8 is like discretized version of that differential equation. And okay, I think if we look at equation 8, it essentially says that for the data object I want to predict what will be its velocity at timestamp t+1, right?
Yes.
And then if we go back to the previous slide, and it used the graph neural network to replace that.
So I think the question is what the GNN function is.
Yeah, it's just a wonder, and it's just a one step. And the related questions like, will this graph neural network be different under different timestamp?
Yeah, so I think they give a very simple kind of neural network, which is just MLP summation of kind of these neighbors here, MLP, where the MLP is like the node embeddings and edge embeddings all concatenated together.
Maybe at that timestamp, so then it can based on that to compute what would be the velocity of the next timestamp.
Yeah.
Okay. Okay, then which is different from Zijie's approach? For Zijie, she wanted to directly use graph neural network to write down the gradient part.
Yeah, so I think they don't really consider the gradient at all. I think this kind of the kind of experiment that they did is I don't think completely unexpected, because first of all, like their GNN isn't that kind of powerful. And second of all, if you notice here, they, in their improved features, they kind of change what this W is equal to according to T. Whereas in the original features, this W is just a constant value. So if you're changing this W with respect to T, you're kind of injecting like even more information about your kind of
or we can think that every time it's just a one step prediction. One step forward prediction. And for Zijie, she can handle much longer term prediction because she really wants to model the dynamics.
Exactly. Yeah. Cool. Yeah. Any other questions?
Okay, I think if no more questions, we can stop here. Thank you, Derek.